content involving gases, but we'll go with gas stoichiometry. I think we did some of that. And remember that really gas stoichiometry does work the same way as regular stoichiometry type problems. You could have, like we talked about with regular stoichiometry problems, you could have basic stoichiometry problems. You could also have a limiting reagent situation. And just like normal, although you may be given some different sort of information, the way that you could determine that it is a limiting reagent situation is if you have enough information to get to the moles of all the starting reactants. But other than that, most of the time, probably going to be more of a basic stoichiometry problem, which means we need to balance the equation. We need to convert to moles. We need to do our mole to mole relationship, which is really the stoichiometry part, and those moles to some other unit. As we talked about, as we did in some of those examples, again, pretty much somewhere in this process, you're most likely going to use, again, that ideal gas law. And that ideal gas law is usually used in 1 to 2 places, or sometimes even both places, but it can be used here. And in this case, this would be an alternative way to get to moles by using the ideal gas law and solving for moles. And at that point, you could basically just pick up like normal, your mole to mole relationship and everything. Probably most commonly, a lot of times you're interested in how much volume, say, of a gas you would collect in a situation. So at the end here is a very common way that we would do a sort of ideal gas law to solve for volume. So you could potentially use it in both places. But most of the time, I would say probably this last spot is where you would sort of incorporate it into. Alternative to that is, again, as well, with that sort of Avogadro's relationship that goes with sort of gas stoichiometry. If you got a bunch of gases here in an equation, and you're at constant pressure and temperature, and you're really only interested in perhaps the volume that you would produce, and you're given a volume, much like we could do a sort of mole to mole relationship between these guys. We can do a volume to volume relationship, like 2 liters of A would give us 3 liters of B. And if you sort of do that in that situation, you can sort of bypass a lot of times using the ideal gas law. But again, it really does have to be that specific conditions of constant pressure and temperature, which is what we see in Avogadro's law. And again, you can sort of bypass it. If you couldn't remember that, don't want to do that, you could still do the ideal gas law. You would probably use it twice in that case, that type of problem. You just use the same pressure and temperature on both sides of the calculation. When you would go here, for example, and here, you just use the same pressure and temperature, and it would work out the same. So, you know, you do have some alternatives in terms of doing that. We also talked about sort of the velocity of gases, and again, it is related to the mass of those guys. So lighter gas molecules will move faster, heavier gas molecules will move slower. And we do see that in terms of temperature, it does affect how fast or slow a molecule of gas will be traveling. At higher temperatures, it will be moving faster. Lower temperatures will be moving slower. We calculated the root mean square velocity. Or the RMS, and the RMS is the square root of 3RT over the molar mass. The R here is the other version of the gas constant, which is the 8.314 joules per Kelvin per mole. And that relationship of a joule is a kilogram meter squared second squared comes into play here, which also means our molar mass does need to be obviously in kilograms. We also at the end there talked about effusion and diffusion. Diffusion, right, is the gradual mixing of gas molecules due to their basically motion. And we have an equation that goes with that, which is like R1 over R2 is equal to the square root of the molar mass of 2 over the molar mass of 1. And again here, we could use this to figure out how fast, obviously, a gas molecule is moving. if maybe we know how fast another gas molecule is moving, or can figure out the molar mass as well. So again, the sort of faster moving, lighter gas molecules, right, will reach the other chemical a lot quicker if you can sort of separate them on opposite sides of each other. And the mixing that would occur, for example, in a chemical reaction, I think we looked at ammonia and HCl, would occur closer to the slower moving gas molecules. Obviously, as it's moving slower, the faster guys could get over there quicker. We also saw a fusion, which is basically the transfer of molecules from one compartment to next through a small opening, right? And it's basically the same sort of formula there. You could also include time over time as instead of the rates, and you could solve for that. We use that as sort of an application and a problem I think we finished up on to help us understand maybe a unknown sort of formula based on the difference in sort of how fast they can sort of fuse versus one side to the next. Any questions on any of that there? All right, the last thing we're going to talk about here in this chapter is real gases. And real gases, unlike those fake gases we've been talking about, they are sometimes referred to as real gases. Now, remember that we did talk about as well the two real main things that sort of make something an ideal gas. And that was the idea that the volume of the gas itself is negligible compared to the volume of the container it's in. And secondly, that there's no real attractive forces or repulsion type forces between molecules. And again, that's why when we did sort of partial pressures, which was another topic we think we talked about last time as well, we could basically treat each gas as if they were in that mixture by themselves, not really with anybody. They're in the container by themselves. That's, there's no real interaction that occurs between them. But that drastically does change at a couple of situations, really high pressures and low temperatures. In those type of situations, you do actually have to take into account both of those things. So you have to take into account the volume of the gas itself, and also the attractive forces and repulsion forces that occur. And if we take the ideal gas law and we solve for moles, we get a nice ratio of 1, and that's sort of an ideal situation as you see here. But as we move out into much higher pressures, we do start to see our repulsive forces and attractive forces sort of coming into play. If we think about really high pressures, that means we have really small volumes, right? Which means in this situation, everybody is pretty much near each other, right? So there's no escaping each other. So that interaction that occurs in those situations is really, really small sort of volume situation because of that large pressure, means that those gas molecules are actually going to be around each other for a lot longer period of time. There's going to be a lot more interaction. So they are going to basically interact with each other. Also at really low temperatures, they're not going to be moving as fast, which means they are going to be staying near each other for a lot longer period of time. So there's going to be a lot more interaction that basically occurs. So if we look at real gases, which is what these are sometimes called, real gases, bless you, do not behave like ideal gases at high pressures or low temperatures. Again, the two things that we talked about there that make an ideal gas really do come into play under these conditions. At low temperatures and high pressures, we do not see those assumptions being correct in terms of the non-interaction and the volume of the gas as well. So when we look at a real gas, because real molecules take up space, the molar volume of real gas is larger than what would be predicted by the ideal gas law under high pressure situations. So this is sort of lower pressure situation. And as we get to sort of our higher pressure this way, we start to see a difference in the molar volume of a gas. A molar volume is at 22.414 liter type of conversion that we talked about. And there is a difference. And again, at really high pressures, we would have, as we talked about, you know, kind of a small volume, right? So now you got these gas molecules in the small space, which means that the volume of the gas is actually not going to be negligible compared to the container, because the container's volume is going to be really small to begin with. So it's like, you know, you put a ping pong ball in a box, right? Under ideal conditions, that little ping pong ball is not going to make up all that volume of a box. But you take the ping pong ball out and you throw like a basketball in there. Now it obviously does make a big difference, right, in that box in terms of the volume of the ball itself. And that's because, again, under these really high pressures, everybody is very, very close to each other and are taking up space rather than they got plenty of room to sort of fly around in. The effect of molecular volume was looked at by our good friend van der Waals, which we'll talk about in the next chapter, which is a lot of what he did was intermolecular forces and how molecules interact with other molecules. And at high pressures, again, that amount of space that's occupied with molecules are significant. So really, van der Waals came up with sort of a correction value for the ideal gas law to sort of take that into account. So this sort of correction for the volume of the gas in the ideal gas law comes into here, and it's basically nRT over P plus N times B. B is what is known as van der Waals constant. And van der Waals constant, there's really A and B are the two van der Waals constants. They are specific for the specific gas you are dealing with. So they do change depending on the gas. And you would look it up usually in a table for obviously the gas you're looking at and which value that you need, A and B. You probably need both if you were doing that. So this sort of correction here for the volume was done to the ideal gas law. But in addition, we also had to take into account what happens again at sort of low temperatures. So again, at low temperatures, everybody is moving very slow, which means as these two guys pass in this can, they are definitely going to be near each other for, again, a lot longer period of time than they would if they were just kind of whizzing by each other, not really staying near each other for all that much time. So what we do see here is we actually see a decrease in the molar volume of ideal gas versus a real gas situation at these low temperatures. So van der Waals came up with sort of a correction value for that as well, for those intermolecular forces. And this is a value here. And that is the correction for those intermolecular forces. As we touched upon last time a little bit, why that's important, again, is if we have this gas molecule in an ideal situation, he's pretty much free to fly around and have collisions as much as he wants. If we start introducing sort of attractive forces between gas molecules, again, if there was some attractive force, that's going to slow down our gas molecule as it's flying around, and it would have obviously a effect on the pressure that would happen. Maybe they wouldn't hit as much, or maybe if they were repulsed by each other, they would hit a lot more. So it would have an effect on the pressure that we see under these sort of real gas situations. And that's what we see in this picture here. Again, in an ideal situation, this guy would be free to just fly around basically and bang the wall, not really worried about anybody else that's involved in there. But with those interactions, it could have a good effect on, or a bad effect, I guess, on the pressure. So this is what is sometimes referred to as the van der Waals equation for non-ideal gases or real gases, and it's basically a scary version of the ideal gas law, but it really is still the ideal gas law, which means in most cases, you still need to make sure everybody's in those same units that we talked about. So again, pressure should be atmospheres, volume should be liters, moles, and obviously our Kelvin. This is a table, and you have one in your book, and usually, again, you would look up this table to find your van der Waals constants. I would say if you ever use a table like this, you should always look at the units of the van der Waals constants, because they may not always be the same units of, liters and atmospheres and stuff like that. So you might have to do some type of conversion. You would solve it just like the ideal gas law. Obviously, maybe you're looking for pressure, or maybe you're looking for volume, whatever it may be there. But again, it is a more specific type of equation. So a lot of times you can think of the van der Waals equation here for real gases as a more specific type of gas equation. The ideal gas law, which we use in most cases, is more of a universal type of gas law, which it doesn't really matter what gas you're dealing with. You could just plug and chug into there. And the reason we don't often use perhaps the van der Waals equation in a lot of situations is, if we go back to sort of the graph here that we saw here at the beginning, it's here somewhere, I think, right? It is, maybe, there it is. Most of the time, right, the pressure that we deal with is about 1 atmosphere, which is like way back over here, yes? And obviously this is about 200 atmospheres of pressure, which we never really get to. And in that little circle, what I circled is probably what most of the cases we have in kind of regular life is going to be. Things are still behaving ideally. If you look at the line, it's still relatively straight at that point. It really doesn't start deviating until we get to these really sort of high pressures and stuff like that. And again, that's why in most cases we do use that ideal gas law, because in a lot of sort of normal conditions, it basically will, any gas sort of behave that way. But if you do have a situation where you have these really high pressures or low temperatures, you will have to sort of move into that real gas situation. Any questions on that there? Because we're definitely not usually around that much pressure in normal situations, hopefully. Yeah. All right, that wraps up this chapter here. We're going to roll to the next one. Let me just find it here. So that is obviously the last bit of information that would be on the exam coming up on. Okay, so we're off here to chapter 9, I think, and we're talking about intermolecular forces. And this chapter also the liquid state. So this would be exam 4 info right about now. Here we go. So really a lot of what we're going to talk about at the beginning of this chapter is about really 2 types of forces, or really one type really, which is intermolecular forces. Intermolecular forces and intramolecular forces are a little bit different. So let's talk a little bit about intermolecular forces first. Intermolecular forces are the forces that hold basically one molecule together with another. So it's basically how one molecule interacts with another. And that can be one molecule that is itself and how it reacts with another similar molecule or exact same, like 2 water molecules, for example, interact with each other. It is also how different molecules interact with each other as well, like a water molecule and, you know, something else like methanol or something like that. And all intermolecular forces pretty much break down to a very basic way that they interact with each other, and that is electrostatically, which means basically the positive negative attraction that occurs. So at some point, one molecule has a positive side, the other molecule has a negative side. And it is that opposite attraction that allows those molecules basically to interact with each other. And that's really the basis of all intermolecular forces, is just that simple positive negative attraction that occurs. It is responsible for the condensed states of matter. It is a big factor, the type of intermolecular force, in things like melting points, boiling points. And the stronger the intermolecular force, the higher the melting point and boiling point is. So the stronger the intermolecular force, the higher the melting point and boiling point is. And the opposite of that as well, the weaker the intermolecular force, the lower the melting point and boiling point. That is because in order to get something like, say, at the boiling point into the gas phase, you got to break that bond between the 2 molecules. And if that bond is relatively strong, it's going to take a lot more energy to break that bond, which means you will have a much higher boiling point. And if that bond is a lot weaker, it's going to take less energy to break it, and you would have a lower boiling point and also a melting point. So these are really the big sort of indication as to, you know, those boiling points and melting points. It also is a big indication in terms of solubility. It is also why certain things are soluble in other things, and also why other things are not soluble in each other, is these intermolecular forces. So as we talk about this idea of like dissolves like, which means things that have very similar intermolecular forces are going to mix really well with each other because they could basically interact the same way they interact with themselves. And things that have very different intermolecular forces means they have no real long way of interacting or maintaining an interaction with one each other, and that's why things are not soluble in each other. So intermolecular forces is a really big idea in terms of those important ways that molecules sort of interact either with themselves or other things. And that shouldn't be different, confused with the other type of force, which we won't focus too much on, but that is what is known as an intramolecular force. Intramolecular force means within the molecule. So this is like within a molecule. So for example, if we had just one water molecule, the intramolecular force is basically the covalent bonding that's happening there, the oxygen and hydrogen bonding to each other on both sides, just sharing of electrons. It is the forces that hold this bond and this bond together within a single molecule. And that should not be confused with when we get, say, two water molecules together. Water being polar, as we've talked about, has a more negative on the oxygen, more positive on the hydrogen side. And that is the intermolecular force. So that would be an intermolecular force. Bless you. And this obviously would be an intramolecular force. And what we know is, with actually just this very simple example of water, the intramolecular force is always much, much stronger than the intermolecular force. And we know that because we've all probably boiled water at some point or heated up water. And what happens when you heat up water is the bond between the water molecules break and you get steam, right? As those water molecules basically separate out. If it was opposite of that and the intramolecular force was weaker, when you would go to heat up water, it would actually break the individual bonds here between hydrogen and oxygen, producing hydrogen gas and oxygen gas, which probably wouldn't be great if you're trying to make pasta and you're boiling the water and stuff like that. So we know just from that, it's a very simple example, intermolecular forces are always much weaker than the intramolecular forces because we usually don't get alphabet soup when we just sort of heat things up like that. Any questions on that? So what we're going to talk about here really, and some different types, is intermolecular forces. So all these that we're going to talk about here are intermolecular forces. And the first type of intermolecular force we're going to talk about is a dipole-dipole interaction. And you might remember dipole, we see dipoles in polar molecules, right? Polar molecules that have overall an unequal sharing of electrons is where we do see polar molecules happen. And because dipole-dipole is the main interaction of how a polar molecule interacts with another polar molecule, is the real main sort of way that these guys interact. So what does it mean when we have a polar molecule? It means we have unequal sharing of electrons overall, and that frankly means there's a dipole moment, and that means that we have a positive side of that molecule and a negative side of that molecule because of the unequal sharing of electrons. And that is all we need for these guys to, again, interact like so. That positive side of one will be attracted to the negative side of another. And molecules that have dipole moments, which are polar, tend to do this. When we do get a bunch of polar molecules together in sort of a solid situation, they do try to really move around a little bit to interact or to really maximize the interaction between opposite charges, right? So no matter what happens, definitely in the solid state, right? In most cases, in the solid state, things are packed in there a lot tighter than in the liquid state or the gas state. So it's going to happen no matter what, that you are going to get some like positives, near positives, but they do try to kind of move around and sort of orient themselves in a way where they do maximize that positive negative attraction, try to minimize positives, near positives, or negative sides of molecules, near negative sides of molecules. So they kind of move around a little bit to, they can find a sort of a comfortable arrangement for that. In liquid, they tend to align in a way that maximizes that attractive forces and again minimizes that repulsion forces. So these are the main type of interaction that occurs between polar molecules and other polar molecules. And again, here in a much prettier picture, you can kind of see they really try to maximize that attractive sort of force, but kind of minimize that positive or negative or positive and positive guys being around each other. Now, another type of sort of force that occurs with polar molecules is an ion dipole force. And much like the name implies, it's an ion and a dipole. So you basically have an ion and a polar molecule coming together. So this is basically an ion and a polar molecule. An ion can be either positively charged, right, or negatively charged. And again, if you have that polar molecule, the negative side would be attracted to the positive ion, and the positive side would be attracted to the negative ion. This is pretty much what happens when we dissolve an ionic compound in water, right? What happens when we take something like sodium chloride, that's a solid, and we throw it into water, we get the sodium ion, we get the chloride ion. And water, because it is polar and it has that positive side and negative side, the negative side of water will go around and surround the sodium ion. And the positive side of water, which is the hydrogens, will come around and surround the negative ion here. So that's really ion dipole interaction. Does a couple of things. This is really how an ionic compound, for example, really does dissolve, and why it is soluble in water, because of that sort of positive negative attraction that occurs. As we talked about, there's so much water in there that it's enough to strip off the ions from each other, right? You need a tremendous amount of water to do that. And luckily the concentration of water is pretty high, so it's able to really pull those ions apart from each other when they're in the solid state. They're kind of like the picture we just saw. All the ions are clumped together, opposites attract. So enough waters are in there to kind of pluck off each of the ions and keep them surrounded. And that also allows it to dissolve, right? Because it creates sort of a barrier between the two ions, because if that barrier was not there, the solid would want to come back together. Basically, those two ions would want to come back together, because an ionic bond before it dissolves is an intramolecular force. It's a really strong force, but just so much water is able to basically do that. And again, we know that happens because when we go take something like salt water, and if you heat up salt water, again, very similar to some of those earlier experiments we did when we put the evaporating dish up on top of the water in the beaker, you would basically evaporate off all these waters if you were to heat it. And that now gives a free path for those two guys to come back together. And that's why you can still see your water. So you'll see your sodium chloride. That's why when you make a solution like salt water, a solution is a homogeneous mixture, right? The stuff's still there. They still retain their identity. It just looks different. It's a physical change because you could evaporate off the water and get your salt back. So ion dipoles is more specific sort of classification of an intermolecular force, where an ion and a polar molecule basically are attracted to one another. Now, what happens for sort of all of our other guys are like non-polar molecules? They use some type of dispersion forces, and dispersion forces are really the forces, truthfully, everybody can use dispersion forces in some aspect or another for a little bit, but dispersion forces are really the main interaction for non-polar molecules. And really, they are the weakest sort of interaction. Dipole is pretty strong. Ion dipole is pretty strong. But dispersion forces are kind of the weakest out of all of them. And that is because, frankly, they have to rely upon something happening for that interaction to occur. And that is very different than what we've just been talking about with like polar molecules. Polar molecules have a dipole moment, which means no matter what you do to a polar molecule, it's good to go. It's got a positive side and negative side. It's good to go in terms of interacting with something else that has positive, negative. Non-polar guys, if you remember, basically means that we're sharing the electrons equally throughout the molecule, which means there is no positive side or negative side. It's kind of like a neutral sort of molecule. So it's not good to go. It's not out of the box. You got to do something to it. So a lot of dispersion forces rely upon something happening for that interaction to occur. And because it relies upon that, it's a relatively weak interaction versus a dipole-dipole interaction where your polar molecules are, again, good to go sort of right out of the box. So one thing that can happen is what is sometimes referred to as an induced dipole. And that's the separation of positive and negative charge in a nonpolar molecule or a neutral atom. And that's caused by the presence of a polar molecule. And there's two types of sort of induced dipoles that could occur. You could have an ion-induced dipole, which means you have an ion like this positively charged. And if you bring a positively charged ion near a neutral atom, the electrons in that neutral atom are now going to be attracted to that positive ion because opposites attract, which means in this normally neutral guy that has no separation of charge, it will temporarily gain a separation of charge because the electrons have now shifted to one side of the molecule versus the other because of the presence of that ion, kind of like a magnet, kind of bringing it towards itself, going to bring the electrons towards that side of the molecule. And now that that normally neutral guy that's nonpolar has this separation of charge, it gives this guy a way to interact with each other, the positive ion and the negative side of that. It is weak because, you know, as soon as that sort of ion moves away, the electron is going to flop back and it's going to kind of break apart. Same thing basically happens, which is known as a dipole induced dipole. And if you have a polar molecule, same thing is going to happen. It's going to really bring those electrons towards the positive side of it, and it is going to give it a way to interact with each other. So for example, you know, if you take like oil and vinegar salad dressing, right? You can mix it, right? And it stays mixed for a while, right? But over the long period of time, can't maintain it, right? And it all separates out and you got to remix it and all that kind of stuff. So that's sort of what's happening here. It gives it a way to interact for a short period of time, but because those nonpolar molecules really don't have that fixed sort of separation of charge, they have no way to maintain it over a long period of time, which is why it's a relatively weak one. This is also why even polar molecules can use dispersion forces in this sort of effect, but it's not their main sort of intermolecular force, but they can interact with each other. Also why kind of like oil and water mixes just a little bit, right? Then it kind of separates out over a long period of time. Now, another way that this sort of interaction can happen, especially what happens, for example, if maybe a polar molecule or an ion is not present and you just got like nonpolar guys and nonpolar guys near each other, is through what is referred to as polarizability. And that is the ability really of electrons in an atom to decide, we're just going to like vacation on this side of the atom versus this side, because they are moving around. So it is possible for those electrons to sort of pile up on one side of the atom versus the other as it's moving around. And what that will do is create what's sometimes referred to as an instantaneous dipole. It's kind of those electrons sort of move one way over the other. And polarizability is the ease at which those electron distributions can do that. So what that means is, for example, if we had two nonpolar molecules having no charge, and just for whatever reason, the electrons in this guy decide to all kind of migrate towards the right-hand side of my circle here, that's going to create in this first nonpolar guy a temporary separation of charge, which once again, if he's still near the other nonpolar guy, it's going to cause the electrons in it to go away from the negative charge. And that will then create a temporary charge in the second nonpolar guy. And now these guys have a way to basically interact with one another. And that is what is sometimes referred to as an instantaneous dipole or dispersion forces, this sort of electrons moving from one side to the next. The reason, again, it's weak and temporary is the electrons decide to come home from the vacation and start moving around and get a little bit more equally distributed throughout the molecule. That interaction is going to basically break apart. So it's not going to be able to maintain that over a long period of time. But this dispersion forces is basically what happens with nonpolar and nonpolar guys. That's how they're able to interact. That's also why a lot of nonpolar guys have very low boiling points and melting points. Because of this type of interaction. That's why organic molecules like methane, propane, butane, those are all gases under normal conditions, right? And they're basically carbons and hydrogens, which is a non-polar bond. And because they use this type of interaction as their main way to interact with each other, it doesn't take a lot of convincing for those guys to kind of get away from each other. And that's why they go into the gas phase. If you take organic chemistry in the future, sorry, but if you do take organic chemistry in the future, a lot of times they throw you in a fume hood in the lab because a lot of organic molecules are non-polar, which means it doesn't take a lot of convincing for it to go from the liquid phase into the gas phase very quickly. And you don't want to inhale all that stuff. They're very volatile because they could kind of escape into the gas phase because of their very weak interaction with each other. Now, the attractive forces that arise as a result of these temporary dipoles are what are referred to as dispersion forces, and they do increase with molar mass. So the larger the molar mass, the stronger the dispersion force would be, the stronger the weaker force would be. So if you have a comparison of two like non-polar molecules and you want to know which one should have the higher boiling point, and they both are using dispersion forces, the one with the higher molar mass would have the stronger our higher boiling point, because more molar mass means more atoms means more electrons, and a greater chance of those electrons kind of moving around and creating these temporary charges. It also gives it a lot more places where interactions could occur. And that means that when you're comparing this weak sort of intermolecular force, the guy that has the higher molar mass will have the larger boiling point and melting point, because they have a greater chance of this occurring and a greater chance of this happening in multiple locations. Dipole-induced dipole are sometimes referred to as van der Waals forces, as we just talked about there with our friend, the van der Waals equation. Here's an example of that instantaneous dipole. Again, just this guy kind of separating out his charge will cause this guy to separate out of charge. And now the positive and negative side will have a way to interact with one another. Now, a special type of dipole-dipole interaction is what is known as hydrogen bonding. And hydrogen bonding is a special type of dipole-dipole interaction. It happens when you have a hydrogen that is bonded directly to either nitrogen, oxygen, or fluorine. So those hydrogens that are bonded directly to nitrogen, oxygen, or fluorine can participate in a hydrogen bond. That is because when we look at nitrogen, oxygen, and fluorine on the periodic table, that is upper right of the periodic table, the most electronegative element is which one? It is fluorine. Yeah, it's the most electronegative element. So nitrogen, oxygen, and fluorine with hydrogen will create a pretty good polar bond between those two. And that's going to give that bond a separation of charge that's going to allow it to interact with something else. That is how water interacts with something else. Again, water being negative, this being positive, that is a hydrogen attached to an oxygen directly, able to hydrogen bond here with this move. Now, you should be aware of a couple of things, which is, let's take a look at a couple other guys here. Can this guy hydrogen bond? This guy can hydrogen bond. That is a nitrogen attached to a hydrogen. That is a polar molecule. So ammonia can hydrogen bond. Can this guy hydrogen bond? This guy cannot hydrogen bond, even though it's got 4 hydrogens, because the carbon hydrogen bond is non-polar, right? So there is no separation of charge that's occurring there. So just seeing a hydrogen doesn't mean that something has the ability to hydrogen bond. It really does have to be a hydrogen that's attached to nitrogen, oxygen, or fluorine in order to do that. By the way, this guy, which is non-polar, should be using what type of force? This guy should be using dispersion forces, yeah. This guy would be using hydrogen bonding. So there really is sort of 3 major breakdown in terms of intermolecular forces, and again, sort of the strength between them. On one end, we have hydrogen bonding, which is the strongest of all intermolecular forces, and that's why things like water and stuff like that have a very high boiling point. And that is for polar molecules. And polar molecules that have a hydrogen bonded to nitrogen, oxygen, or fluorine. Has the ability basically to hydrogen bond. The next strongest is dipole, and any version of it there, ion dipole and all that. And that is also pretty strong. And that is for polar molecules that cannot hydrogen bond. So if I had something, I don't know, say like this. That is a polar molecule, yes. It doesn't have the ability to hydrogen bond, so it would use dipole-dipole interaction in this case. Again, it does have a hydrogen, but that's a carbon hydrogen, which is nonpolar. So that would be able to use dipole-dipole interaction. And the weakest of all interactions is the dispersion forces. And again, these are all intermolecular forces. And this is the weakest, and it is the major force that is used for nonpolar molecules and how they interact with themselves and others is our dispersion forces, like this guy here, right? And again, hydrogen bonding, which really is a special class of dipole-dipole interaction. It really is dipole-dipole interaction that's happening, but it is oftentimes sort of classified separate from itself, from dipole-dipole. But hydrogen bond and dipole-dipole both involve polar molecules. And again, the major difference between a polar molecule and a nonpolar molecule in the sense of intermolecular forces is, as we talked about, a polar molecule will have that dipole moment. It's got the positive and negative side. No matter what you do to it, that water molecule is floating around ready to go with the positive and negative side. It's ready to interact. A nonpolar molecule has no charge, so it's floating around neutral, if you will. It needs something to occur to help it sort of interact. And again, that's what makes it a lot weaker than something that involves a polar molecule like dipole-dipole or hydrogen bonding. Any questions on the differences in intermolecular forces? All right, and there's some intermolecular forces of hydrogen bonding happening. All right, so let's talk a little bit about the liquid state and some properties of liquids as we go through it. Liquids obviously are the state of matter where everybody is relatively close to one another. They still have enough sort of energy to sort of move around each other and past each other. And again, that is why they are fluids, right? They're able to kind of flow like a liquid, obviously, because of that movement that doesn't happen in solid when everybody just sort of locks into place and becomes rigid, right? And stuff like that. Viscosity is the resistance of liquid to flow. It is related to intermolecular forces. So water has a low viscosity and motor oil has a high one. It does increase with temperature. So as you increase the temperature, the viscosity obviously gets less there as you have a lot more energy, things able to move a lot more, right? Or past each other, they gain a lot more sort of energy. Now, when we talk about water, and other sort of solutions or substances, there are a couple of types of forces we sometimes talk about. Cohesive forces are the forces of attraction between molecules of a single substance. So that is basically like hydrogen bonding in water. It is how one guy interacts with another. Adhesive forces are the forces between basically two different molecules. As we will see, this is basically what accounts for like the meniscus that we see when we put like liquid substance in a glass surface. Now, surface tension is the elastic tendency found at the surface of a liquid. Energy is needed to expand the liquid surface. It is higher for liquids that have a greater intermolecular force. So, for example, if you kind of lay a paper clip there on some water, you can get it to sort of float there without breaking it. Surface tension is greater when in water than other common liquids because of that hydrogen bonding. That's because there's a really strong attraction between water molecules to the side of each other and down, so it makes that surface tension really strong. It is also why some bugs and stuff, right, can walk on water, right? Just kind of walk across it because of the surface tension that is there. And that is because a water molecule, for example, up on top feels the attracted pull to the right, feels the attracted pull to the left and down, right? So that sort of expands the surface really, really tight. And that's different than, say, a water molecule below the surface. It's kind of feeling the pull all around sort of equally. The guys at the surface have nothing above it to sort of pull it up, right? So you just get this kind of pulling this way and this way, tightens up the surface, right? And creates a dribbling effect when people try to pour things, right? That's why when you pour something, you should commit to the pour so you can break that surface tension, right? If you're kind of slow and careful, you end up making a bigger mess, right? Always, because you're like, it starts dribbling all over the place because you can't break the surface tension. Take it and just pour it, break surface tension, you'll be all right in most cases. So good skill to know, just pour the thing, don't play with it all day and let it drip all over the place. So he'll never break that surface tension of the surface there. Now, soap and detergents are sometimes used for a couple of things, but it's also used to, kind of spread out water, if you will. So if you ever, for example, just threw water on your car, there's some type of wax maybe still in there. It's in fairly good shape. A lot of times you will see the water start to bead, right, rather than sort of spread out. And that is because, again, the strong surface tension will happen also on umbrellas as well, right? It'll sort of bead off of the umbrella. So that strong surface tension prevents really water from spreading out on those non-polar sort of surfaces. Again, that non-polar surface is going to be using dispersion forces. You got your hydrogen bonding, not really going to mix. So it's just going to kind of separate out from one another. So water just tends to bead. That's why when we do wash your car, we hit it with water, then we hit it with soap, right? And we put soap on there. And soap is a long molecule that basically has two parts. Soap has a non-polar part, and these are all just carbons and hydrogens back here, these little scribbles. And this is the non-polar part of soap, and sometimes referred to as the non-polar tail of soap. And soap has a polar part that looks something like this. It's a polar part, kind of like a carboxylic acid, and that's sometimes referred to as the polar head of soap. And what happens when you put soap in there, it's able to basically break out that surface tension because the polar part of soap is able to interact with the polar water. So it's able to kind of get in there between the water molecules and sort of spread it out. Also, though, does leave the non-polar part in case you are washing your car, because dirt is non-polar and it will grab up all the non-polar dirt and get it in there. And that will allow really your kind of water and everything to spread out, right? So if you ever take soapy water, right, and you put it on your car, it just kind of goes out like that because of that. The old Dawn dish detergents commercial, when they put a drop of it into some water and it goes, all the dirt kind of spreads out and everything spreads out. It's the same sort of idea that occurs there. And that's also how we use soap and just regular soap, right? Dirt is non-polar, so dirt gets trapped over here at the tail. We wash off the soap with has the dirt trapped, and water and that part of soap are soluble in each other, so it goes away. Now, adhesive and cohesive properties. Again, when we do take a glass tube with a small diameter, we put it into water, the water will rise through capillary reaction and basically will kind of draw up the tube. And that's because water forms hydrogen bonding with basically the glass tube that's there. And that is what accounts for the meniscus that we see. And, for example, in water, we see that curvature of the liquid drawn like so. And that's because what happens here is there's a stronger attraction between the water and the walls of the container, and it causes the end side of water in that tube or container to start to rise because of that attraction, right? And that's why we read from the bottom of the meniscus in most cases, because truthfully, if there was not that attraction, the actual volume would be at the bottom, right? It would just be a straight line up there. There wouldn't be the curvature if there wasn't that attraction. So the true volume that you have, so we see in the middle where we don't have that interaction happening with the walls of the container. And that's why we read from the bottom of the meniscus. Not all substances sort of work that way. In this case, the attraction between water in this container is stronger than water in itself. But if you took something like mercury, which we might have talked about as well, mercury actually goes the opposite way. And that's because the attraction between mercury and itself is greater than the attraction between mercury and the glass tube. And what happens is mercury kind of comes in on itself, and we get this sort of opposite meniscus that occurs. And the same reason in this case, we would actually read from the top of the meniscus, because if there wasn't that attractive force, the real volume would be down here at the top in this case, because it goes the opposite way around. So this has to do with obviously the adhesive versus cohesive forces, and the attraction between either itself or something else is what causes that meniscus and that curvature of those liquids that we see. Now, vapor pressure is another sort of aspect of a liquid, and the tendency of a liquid to vaporize is what is referred to as the vapor pressure, and also known as volatility. And it does increase with temperature. So liquids in an open container will evaporate completely because the air diffuses it. It is also why when you spill a little something on the bench, that's a liquid, at the surface of any liquid, there is a constant exchange of evaporation and condensation happening. We got faster moving molecules jumping out of the liquid to go into the gas phase. We got slower moving guys dropping back in for a swim to go back into the liquid phase. And this is constantly happening at the surface of any liquid. So if we put a little bit of water on the bench, you would have this process occurring. The difference though is if you have it kind of out in the open is there's air. And air will push those molecules away, which means they're no longer available to drop back into the liquid phase, and they start to evaporate, right? If I take that same liquid and put it into an open beaker or a cup or whatever it may be, it will evaporate, but it'll take a much longer time, right? Because it's kind of trapped on top of each other, right? So there's a lot more volume sort of trapped that has to kind of work its way out of the thing. And that's why it takes longer. And clearly, if you put a lid on it, right, you're going to prevent the evaporation, right? Because it has no escape route. If you sort of cap that thing up, it has nowhere for those guys to basically go. So the gas molecules above a liquid is what is known as the vapor pressure, and it is related to intermolecular forces. So things with really low intermolecular forces or weak intermolecular forces will have a higher vapor pressure. And that is because if they have a weak intermolecular force, it's going to be much easier for them to go into the gas phase, and thus you would have a lot more gas above the liquid, and you would have a lot more vapor pressure. Obviously, those that have a lower vapor pressure means they probably have a little bit stronger intermolecular force, which means you're going to get less gas molecules above the liquid and a lower vapor pressure. The vapor pressure of a liquid at a given temperature is determined by the intermolecular forces. Again, the larger intermolecular force, the lower vapor pressure, because they're going to kind of stay together, because they're going to be interacted and locked into place. Not a lot of them are going to escape the liquid part and get into that gas phase. And that's also what we oftentimes will see if you really look closely at, say, a liquid in a container, you put like a stopper in, you will typically see the overall volume come down a little bit. And that's because once you put the liquid into a container and you do put obviously a lid on it, you're going to eventually at the very beginning get a pretty strong rate of evaporation. These guys are going to start to evaporate, right? And as they try to escape, there's really nowhere for them to go. So they're now going to get some condensation that's going to occur. Those gas molecules are going to drop back down into the liquid. And eventually you will reach equilibrium, where the rate at which they jump out of liquid will equal the rate at which they drop back into the liquid. And that usually will result in a little bit more vapor than you started with in that thing. And you'll typically see a little bit of a decrease in the liquid level there, because before you put it in, or when you first put it in, there's really no evaporation, and then it all really starts, right? So you're going to get they're going to get stuck in the gas phase above the liquid, and that's going to cause a little bit of the liquid level to drop down. Clearly, it won't completely evaporate because it has no way out of that thing, as long as you don't open the lid, I suppose, or keep it open. Any questions on that there? Now, we can't calculate these things with the equation here, and that's the natural log of our vapor pressure at the first temperature divided by our vapor pressure at second temperature, delta H of vaporization. That's the heat of vaporization, and we might have touched upon it, but if not, let's touch upon it a little bit here. The heat of vaporization is the process where we go from liquid to gas, or gas back to liquid. And when we do these processes like liquid to gas, or gas to liquid, or even solid to liquid, liquid back to solid, it occurs at the same temperature. So for example, this would occur at the normal boiling point of a substance. And there's a certain amount of energy required to do nothing more than take something in its liquid state to something in its gas state, or vice versa, take something from its gas state to its liquid state without changing the temperature. So for example, for water at 100 degrees Celsius, that is where that occurs. 100 degrees Celsius. The delta H of vaporization is something like 2260 joules per gram. So it takes about 2260 joules per gram of water to convert it from liquid to gas, or gas to liquid without changing the temperature, just solely do that conversion that occurs. It takes a lot of energy to do it at the vapor pressure, or the boiling point. More energy than it takes to go from solid to liquid. It's about 333 joules per gram for water at the solid to liquid, liquid to solid. That is because at this point, you're going from liquid to gas, where they're completely breaking apart from each other, right? They got to completely get away from each other, are coming back together, as opposed to as we go from solid to liquid, where they're still relatively near each other in both of those states. Nobody's completely breaking apart from each other. Ours, our gas constant, is the one that involves energy, and our temperatures here do need to be in Kelvin. Also, it's important to note that these two guys can create some trouble in terms of the calculation. A lot of times the delta H of vaporization, or just delta H in general, is given to you in kilojoules, and R is in joules. So there is that sort of 1,000-fold factor a lot of times that happens that you have to watch out for, so that you can do the calculation hopefully correctly. So let's take a look at this one here. The vapor pressure of water at 25 degrees Celsius is 23.8 torr, and the heat of vaporization is 43.9. Calculate the vapor pressure at 65. So if we use our equation that we just saw on the previous slide there, and that is our vapor pressure at T1 over vapor pressure at T2, delta H over R, 1 over T2 minus 1 over T1. All right, so in this case, we have the vapor pressure at 25 degrees. So T1 would be 25 degrees Celsius. Our vapor pressure there for our first one there would be 23.8 torr. We have our delta H of vaporization, which is 43.9 kilojoules per mole. Our R, we always have 8.314 joules per Kelvin per mole. And we want to know what is the vapor pressure when we go to 65 degrees Celsius. So if we put all that in, I find my calculator here somewhere. There it is. So we'll go natural log here of our vapor pressure at the first temperature, which was 23.8 torr. We're looking for our second vapor pressure, equals our delta H, which is 43.9. What I'm going to do is actually multiply it by 1,000. And what that is going to do is convert it to joules rather than kilojoules. So I'm in the right unit. The reason I need to do that is my number here is in joules. That way, again, you're not off by a factor of 1,000, which is a common thing. We're going to do 1 over our second temperature there in Kelvin. So that's 65 plus 273 gives us 338. And try to squeeze it in here. 1 over our initial, which is 25 plus 273, 298. Got it all. All right, if we clean up the right-hand side there, 1 divided by 338 minus 1 divided by 298 times 43.9 times 1,000 divided by 8.314. That's going to give us the natural log of 23.8 over P2 is equal to minus 2.0969. To get rid of the natural log on your calculator, you need to take the E of both sides. When you take the E of this side, it just gets rid of that basically, and that will get you 23.8 over our pressure. And if you take the E of this side, gets us 0.12283343. We're going to multiply P2 to the other side and divide the 0.122 to the other side. That will give us that P2 is equal to 23.8 divided by 0.1228343. And let's see how I did here. Ends up with a P2 of 194. That's good. All right. It would have been embarrassing if I got the wrong number, but you know, it happens. But so we got 194 in this case. Any questions on that calculation? So here you can see it doesn't really matter the pressure as long as they are the same units of vapor pressure. The main thing I would say that most people would screw up on this calculation is Kelvin. And these units, again, being off by that factor of 1,000. So very common. Delta H values are given in kilojoules and that R is in joules. So you got to do one of the conversions. You can also convert the R to kilojoules if you wanted to. That works out obviously the same. Any questions on that? What we also see in terms of our vapor pressure is a couple of things in this problem. At 25 degrees Celsius, the vapor pressure is 23.8. We increase the temperature to 65 degrees Celsius. That means everybody in that solution gained a lot more energy. That means a lot more molecules can escape to the gas phase, and we see a much higher vapor pressure. That would indicate there's a lot more gas molecules above the liquid at 194 versus 23, right? So that increase in temperature allowed a lot more of those guys to escape the liquid phase and be in the gas phase above the liquid. We'll talk a little bit about boiling. Why not? Good talk. So when a liquid is heated, obviously to a high temperature, bubbles start to form and beneath the surface. And if these bubbles can escape to the surface, it is known as boiling. And that is what happens when you really get bubbles that escape, and not what you see that if you ever really maybe look closely at water in like the lab, or when you make pasta and you're boiling some water, when you first hit the water with the flame, usually oftentimes we'll see a bunch of like dots and stuff like that, and people go, oh, it's like boiling, or right off the bat I got all these bubbles sort of occurring. And it's really not boiling obviously at that point, because you just put the heat on it like a second ago. That is really the solubility of things like CO2 coming out of the water really quickly because of the big change in temperature. So it's obviously not bubbling or boiling. It really is not going to boil until it does start to sort of bubble. And the idea there is at some point you will fill up these bubbles with gas molecules. And if the pressure inside is less than like the atmospheric pressure and all that stuff pushing down on it, your bubble is going to pop before it gets to the surface, right? Which is like you see the occasional bubble kind of come and then pop, right? And it's not really truly boiling at that point. It's starting to heat up and getting there. It's not until really the pressure sort of inside there can handle the external pressure, right? It's equal to or maybe a little bit greater than that, it's able to stay a bubble, right? Until it gets to the surface, where clearly it's not going to handle that pressure outside there and is going to sort of burst, and that will release obviously the steam in the case of water, right, as coming out the top and stuff like that. So as you start to boil, and obviously this occurs at the boiling point of a substance, when that pressure of the vapor inside those bubbles, you know, sort of equals that sort of atmospheric pressure or a little bit greater than what is pushing back down on it, you will get that thing to boil. And that's those good, really big bubbles that you see as the thing starts to boil. Now, what temperature something does start to boil is dependent on temperature and pressure, and we'll see some of that a little bit later on. But that's also why when you're in different states, like stuff at high elevation, right, pressure is different than at sea level, and things can boil right at a different temperature than you normally would expect it at, say, sea level, because of that difference in the pressure. Raising the pressure increases the boiling point. For example, a pressure cooker. The tight lid on a pressure cooker holds the pressure of the vapor above the water, resulting in an increased boiling point of the water, and also allows it to sort of heat a little bit more. Lowering the pressure will decrease the boiling point. So here the water will boil at, say, at 120 degrees, because you got that pressure of everything kind of being trapped in there, can't escape, and it will cause everything to sort of boil at a little bit higher of a temperature. Now, boiling is actually a cooling process, which seems kind of weird for a lot of people because it's like usually heat involved in that process and fire, but it actually is sort of a cooling process in a sense, because it is cooled from the top just as fast as you heat it from the bottom. That is why when you look at your thermometer in the laboratory, right, it doesn't go much past 100, right? And you would think, all right, if I'm boiling this thing and I keep heating it, it's going to go past 100, right? And it doesn't, or it shouldn't in most cases. And that is because it is being cooled from the top just as quick as it is being heated from the bottom. So at some point, it will maintain its boiling point at that point. So although you are heating it here, you are cooling it here, the solution. And that is why, you know, when you do hit, say, the boiling point, the temperature should pretty much maintain where it's at, right? It doesn't continue to rise. So when you have a boiling beaker of water, like you did in the fume hood, it doesn't just keep going, right? Higher and higher than 100. Probably maybe they didn't get to 100-ish, depending on the pressure, but it won't continue to boil and boil. That's why, obviously, when you look at a thermometer, it doesn't go much past that on most of the ones we use, for example, in the laboratory. Now, when we talk about phase changes, the process of going from liquid to gas is called evaporation or vaporization. And in the end, that is an endothermic process. You need to put heat and energy, obviously, to do that. That allows the liquid molecules to gain enough energy, basically, to get away from each other and go into the gas phase. Condensation is the opposite, where we take those gas molecules and basically remove energy. So that's an exothermic process. Once again, as I mentioned a second ago, this does occur at the same temperature, that process, and it is the normal boiling point of a substance. So again, for water, that's 100 degrees Celsius to do that. And again, there is that constant exchange that is occurring. When you take something, for example, like water, it's not until you get really above 100 degrees a little bit that you really do sort of transition fully into sort of the gas phase. Not until you're a little bit below 100 degrees that you're kind of in the liquid phase. Again, right at 100 degrees, you basically have both phases in equilibrium with each other. And again, it's going to be an endothermic process, or a positive sort of energy process going that way. And it would be an exothermic process, or a negative process going that way. As I mentioned, for water, the delta H of vaporization is about 2260 joules per gram. So if we were going from liquid to gas, it would be a positive 2260 joules per gram. If we were going the opposite way, not grams, gas to liquid, it would be a negative 2260 joules per gram. So the energy required to do the transition, the number's the same numerically both ways, but the sign is different, whether if it's an exothermic or an endothermic sort of process that's occurring. Now, as liquid molecules basically escape that phase, they do take with them their sort of kinetic energy. And what that does is sort of lower the kinetic energy of the water, for example, right? All these fast moving gas molecules going out of the water, taking the energy with them, lowers the energy of the water. As a result, though, it does take a lot of energy to escape. So as they escape and break all those bonds to get out into the open air, they're actually going to be moving a lot slower than everybody else in the air. And they're actually going to lower and slow down the energy of the air outside of the liquid. So overall, it's sort of a cooling process as you're kind of removing energy and adding slower moving guys to faster moving guys, so lowering things. So again, it's sort of a cool sort of process in terms of energy as well. So water cools, the evaporation rate decreases. That is also why, like when we have Very well drawn. That's a hand, by the way, with some water on it. Use some imagination, it'll be okay. But we have some water on ourselves, like when we go swimming in 400-degree temperature like we're having currently, right? And you get out of the pool, you feel cold, and that's because you have a lot of water on your skin. What happens when you have a lot of water on your skin is the process of evaporation increases, right? And what happens is you are the source of the energy for that. So all the energy from your body goes to the process of trying to evaporate off the water. That makes you feel really cold, right? And that is what happens. And that's also why we start to sweat, right? When we get overheated, we start to sweat because that creates condensation, that creates liquid on our skin, increases the evaporation process, right? Cools our body down as it's releasing all that energy to sort of cool us down. So evaporation is a cooling process in that sense. It's also why, for example, when you do take a shower, right? And as you're taking a shower, there's a lot of steam, right? And a lot of steam means that you're going to get a lot of condensation going to occur. That's why your mirror gets all wet, right? And all kind of when you take a shower. And condensation means that as we go from gas back to liquid, that's a exothermic process, right? Which means it's releasing a lot of heat and energy, right? As you got all that kind of steam going on. And your body is the recipient of all that energy, right? Because it's standing in the middle of it, I imagine, at that point. And you feel warm, right? When you're taking that kind of hot shower or you're in a hot room. So you're gaining all that energy. Then you shut off the shower and then you feel really cold because now you have a lot of water on your body, right? And you got the increased rate of evaporation, which makes you feel cold. So these are what explains what we normally see in a lot of cases. Fast moving water molecules tend to bounce off one each other in liquid. So when those slower moving vapor molecules condense into the liquid phase, hydrogen bonds are made, and again, energy is released. So that sort of condensation, a lot of hydrogen bonding happening with water molecules, releasing that energy that you pick up and you feel warm. So condensation, again, although we sort of envision it as maybe cold and water, is a warming sort of process in that sense, as it is warming everybody up from all that energy is being given off. Now, this is the molar heat of vaporization and condensation. That's the same number really as the 2260 joules per gram that I put up there. That's in kilojoules per mole. And again, that is used at the phase change that occurs between liquid and solid. It is a different value, by the way, obviously, if you're talking about a different substance. So these numbers here are specifically for water. If you were talking about some other substance, they would have a different heat of vaporization when you do that. All right. So this is sort of what we talked about again. If they're equal, you feel no change in body temperature. So if you're at that nice equilibrium point of evaporation and condensation, you're not going to really feel any net difference in energy that's occurring. And obviously, if condensation exceeds evaporation, you're warmed. And if evaporation exceeds condensation, then you're cool. It's also how those hot and cool pads work as well, right? When you break it, it does a chemical reaction, right? So you put it on there to feel hot, right? It's a reaction that's exothermic and release all the energy into your skin. And obviously, if you break it and you put it on there, it's an endothermic reaction. It's going to need to suck out all the energy from your skin and you feel cold. So that's how those type of things basically work. Now, freezing and melting also is a phase change that occurs, and that is going from obviously solid to liquid, or liquid back to solid. That is the normal freezing point or melting point of a substance. This also occurs at the same temperature. So, for example, water, that is 0 degrees Celsius where that occurs. And at exactly 0 degrees Celsius, you basically have both phases in equilibrium with each other. So like ice crystals, you got a little bit of solid, you got a little bit of liquid sort of happening, much like up on top there in terms of boiling point at the melting point. It's not until you get, for example, water a little bit above 0 degrees that you have liquid water, not till a little below 0 degrees that you have ice. There is a delta H of fusion, is the energy required to change a substance from, again, liquid to solid or solid back to liquid. And for water, it's roughly, give or take, 333 joules per gram. And you can see that is a much lower amount of energy that's required to do that phase transition going from solid to liquid than it is going from liquid to gas, which is about 2200 joules. And again, it's because as you go from solid to liquid, or even liquid back to solid, the molecules are pretty much still near each other. They're not completely breaking apart from each other. And when we go from that liquid to that gas, they are completely breaking apart from each other. So it takes a lot more energy to do that. Now, to get water at 0 degrees, we need to release the energy. To get liquid at 0 degrees, we need to apply energy. So obviously, much like I think we probably talked about before, going from solid to liquid, that's an endothermic process, putting energy in. If we're going from liquid back to solid, that's an exothermic process, which would be a negative value for energy, and that is releasing the energy. And this is also why, as you can see kind of in this picture in terms of water, water is an unusual substance because of that hydrogen bonding and that really strong intermolecular forces. When they actually do get into the solid phase, they don't get so close to each other because of that really strong hydrogen bonding. It creates a lot of these open spaces between the water molecules, and that is why the density of solid water or ice is less than what we see in liquid water. They have a little bit more energy. They're allowed to kind of get a little bit closer to each other, but they really do keep their distance when they get into the solid phase. That creates a much larger volume for ice, right? And density is mass divided by volume, which means that number is larger, which means the density is smaller, right? And that's what happens in the case of ice. And that's an unusual sort of characteristic for most substances. In their solid phase, they're actually more dense than in their liquid phase. So water, because of that hydrogen bonding, is a little bit different in terms of the way it interacts. Now, sublimation and deposition are the process where we go from solid directly to gas and we skip the liquid, or gas directly to solid and we skip the liquid phase. That's sublimation, going from solid to gas, deposition going from gas back to solid. Again, it is a endothermic process going in this direction, exothermic process in terms of energy going in the opposite direction. Same idea here. There are certain things that will go directly from solid to gas without needing the liquid, and dry ice is the most common example of that. Dry ice does that. Dry ice is not really water, right? It is carbon dioxide. Yeah. So dry ice is actually CO2, is not water. And CO2 under normal conditions will hop right from solid directly to gas, no liquid cleanup, right? Which is why sometimes people use it. Also super, super cold, right? It will burn you. Also used to get rid of things on your skin sometimes, right? They burn it off with dry ice and stuff like that. Never want to touch dry ice with your bare hands. That hurts. I know it does hurt a little bit. Yeah. There is that energy to do those phase changes, as we talked about, the heat of fusion. That's the 6.02 number, which is sometimes used for water. And that is equivalent to the 333 number we've been talking about as well, or 335, give or take your book, whichever one you look at. Energy required to do that is our heat of vaporization. So when we look at sort of the transition of energy, if we look at sort of a heating curve and a cooling curve, which is kind of the same thing. And if this was ice, this was liquid water, and this is steam up here. This would be like 100 degrees Celsius, which is our boiling point. This would be 0 degrees Celsius, which is our melting point. So when we look at sort of these transitions, and I didn't draw it perfectly here, but these are supposed to be plateau lines here in these two spots. That means that the temperature is not changing, but the phase is changing. And this is where we would use our delta H of fusion between our solid and our liquid. This would be our delta H of vaporization between our liquid and our solid. Now, if we were to change the temperature, but not the phase, which is what occurs here, which is what occurs here, and what occurs here. Those are all places where it's the same phase, but the temperature changes. If we want to know the heat and associated with that, that is something you might have learned about in the previous class and we'll learn about in the next class because they've taken it out of this class, but that is Q is equal to ms delta T. That's our specific heat equation, yeah. Where Q is the heat, M is the mass, delta T is our final temperature minus our initial temperature. Actually, one of the few places where we could leave it in Celsius. And S, or some books use SH, or some books use C, whatever it is. Those are all the specific heat capacities. And that's the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And for water, the specific heat capacity is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. And that's for obviously liquid water here. So if you ever had to do a calculation, which you might in the next class, again, since we don't really do it in here anymore, you would use specific heat capacity equation for any time that you're in the same phase but change the temperature. But anytime when you are the same temperature and change the phase, it will either be a heat of fusion, heat of vaporization sort of calculation, where you just take the grams basically and times it by the energy required to do that. The higher the specific heat capacity, the more energy is required to change 1 gram of a substance by 1 degree Celsius. Water has a very high specific heat capacity at 4.184. For example, some metals are like 0.2 joules, per gram per degree Celsius. And that's really what the units are referred to here. That's the energy required to change 1 gram of the substance by 1 degree Celsius. Water has a very high specific heat capacity, which is why people get a little concerned when the ocean water goes up just a little bit of degrees, right? People go, oh, it's just a little degrees, but it takes an enormous amount of energy to raise that body of water that much of a change in temperature. So that's why people get concerned about the warming of water, because it takes an enormous amount of energy just to move it, 1 degree Celsius and stuff like that. So something to keep in mind. And I think we will lay it up there for today, I think.